Hello everyone. Today we will study about recursion. So if a program allows to call a function inside the same function, then it is called a recursive call of the function. So what I mean is, let's understand it by an example. So suppose there is this function void function with some parameters int a in C. And this function calls a function which is nothing but itself. So it's called its own function a with some parameters. So this is a recursive call in which a function is keep on calling itself. Okay. So to understand this concept in detail, we will look at some very easy examples which we will try to solve using recursion. So the first example we are going to look is Fibonacci series. So in Fibonacci series, the first two terms are 1 and 1, and the third term will be the sum of the previous two terms. So it will be 1 plus 1 equal to 2. So the third term will be 1 plus 1 equal to 2. The fourth term will be the sum of the previous two terms, which is 1 plus 2 equal to 3. Similarly, the next term will be 2 plus 3 equal to 5. So if you see this recursive pattern here, right? So if this each term of the Fibonacci series let be represented by fi, so fi is representing the ith term of the Fibonacci series, then f of I is nothing but sum of its preceding two terms, f of I minus 1 plus f of I minus 2, right? Now this is how we can represent this Fibonacci series. So if you want to try to do this using loop, it is very simple because you will just start. So let's say we want to find the nth term of the Fibonacci series. So we take n as an input. Okay. So suppose we take n as an input, and whatever the value of n is, we want to find that particular term in the series. So it will be very easy. If n is equal to 1 or n is equal to 2, the term will be 1, right? This will be a term. So just return 1. Else we can use a simple loop for I equal to 3, I less than equal to n, I plus plus. And since it is a series which depends on its previous two terms, so let's say the previous two terms is here. So let A represents the I minus 2 term and B represents the I minus 1 term. So here and C be your current, like the ith term. Okay. So A is your representing f of I minus 1, B is f of I minus 2, B is representing f of I minus 1, and C is representing your f of I. Okay. So this is just for understanding purpose. Then here we will try C is equal to A plus B, right? This is my ith term. And for the next loop, this A and B has to be updated. So now B should point to C, so the value of C, and A should, sorry. So now the value of C should be copied in B, and the value of B should be copied in the value in A for the next term. So if we try it as a dry run, so we see that, so we see when I is 3 What were the values of A, B, and C? Okay. First, let's complete this code. So it will be C equal to A plus B, and B A equal to B, and B equal to 3. So we try to understand this. It will be I is 3. Initial value of A and B was 1, 1. We got a value of 1 plus 1 equal to 2. And then the value of A becomes the value of B becomes the value of A, and the value of C becomes the value of B. So when next loop is we go with I equal to 4, C will take this value of A and B, which will be 1 plus 2, and will give you a value of 3. And will update accordingly the value of A. So now this 1 will become the 2, and this 2 will change to 3, and so on. So this is an iterative solution in which we have simply used loops. But we can also do the same thing using functions or using recursive functions. Okay, so if we try to look at this formulation of Fibonacci series here, we see this itself is doing nothing but making so if let's say we define a function which returns you the ith term of the Fibonacci series. So if you pass I as an argument to the function, it will return the ith term. So it's simply this statement itself tells you what your recursive function has to do. So the ith term computation actually needs the I minus 1th term and I minus 2th, I minus second, like I minus 2th term. So for that, what we will do is the function which is finding the ith term will actually make a call to itself by changing the argument to I minus 1 and I minus 2 respectively. Let's look at this example in detail. So what I mean, suppose I have this function int Fibonacci, which takes the argument int n. So n is specifying the term of the series we are interested in. So eventually what this function has to do is this function has to call itself, but with decreased value of the argument. So n minus 1 will now refer to the n minus 1th term, and f of n minus 2 will represent the n minus 2nd term. And this is what this function is supposed to return, right? So if you just think for this statement, what it is saying, this f of n minus 1 will be returning you the n minus 1th term, right? N minus 1th term. And this f of n minus 2 will be returning you n minus 2 term of the series. And the sum of this is nothing but the nth term, which this function itself will be returning, right? Now, let's look at the complete function here. So if you see here, so this is just a simple function. So we have defined int recursive Fibonacci, in which n is defined as the argument, and n is the argument which defines which particular item of the series we are interested in. If n is 1 or 2, we simply return 1 because this is something which is fixed, and this particular condition is called the base condition. And otherwise, it will call itself with the changed argument, which will be like n minus 1 and n minus 2. So to understand this function, let's do a simple try run. Okay. So here, so we have this void function which takes the argument int n. Now, if n is equal to 1 or n equal to 2, it will not make any call to itself, but return a very constant value. So that signifies that will be the end to the recursion we are doing here. Otherwise, it will return function n minus 1 plus function of n minus 2. Okay, this is the complete function. I've copied here to understand it in detail laboratory. Now try to understand this function with n equal to 4. So if we pass this function, the value 4, what will happen? Function of 4, since n is not 1 or 2, it will return this. So it will make a call to function of 3 and function of 2. Now function of 3 is again neither 1 or 2. So it will again call function of 2, function of 1. So function of 2, so when you see this function and you see a base case, the value of n equal to 2, it returns a constant value. So this is where the value returned by so here this function returns a constant value of 1, and this function also returns a constant value 1. So please note that here the recursion has stopped. It's not going further. If we haven't added this condition, which is known as the base case of this function, then there would have been no stop to recursion. It will keep on calling itself again and again and again, and it will get endless recursion, right? So base case is similar to this limiting conditions in loops, right? So this limiting condition which we have here is what we call similar to this base case in recursive functions. And because of this base case only, the recursive functions, there will be a point when this recursion will stop and you will get some value. So now here these two values have been returned, 1 and 1. And this function 3, what it will do, it will just add and it will return a value of 2, right? So now this function returns a value of 2. Similarly, function 2 returns a value of 1. And these values 2 plus 1 will be added here and it will return a value of 3. So if we look at the Fibonacci series was nothing but 1, 1, 2, 3. So the fourth element was 3, which is being finally written by function of 4. Okay? Please note that this base case is extremely important. Without this, there would have been no stop. So suppose if we don't have this base case, okay? So in that case, let's say we don't have this base case, then this will call itself function of 1, function of 0, which will call itself is f of minus f of 0, f of minus 1, and this will keep on going without any stop. So eventually there will be no memory left to allocate to so many functions and your program will fall. So always whenever you are using a recursive function, make sure you have some base case involved. Also, here it won't be a void. Here it won't be a void, it will be an int because you're returning that value. And let's look at another example of recursion. Another example is using strings. So we will check whether a given string is a pallindrome or not. So before proceeding further, first understand what is a pallindrome string. Consider any string, let's say 12. So in this string, if we reverse it, it becomes E M O C L E W. And this string and the reversed string is not same. So it's not a palindrome string. However, if we have something like this and we reverse it, it will still be same as the original string. Such a string is known as a palindrome string. So how can we check whether a string is palindrome or not? A very simple way is, let's suppose we have any string. Let's say we have this. Okay. Now, We can try to do it character by character. So let's suppose take the first character from the beginning and check it with the last character. Since these two characters are same, so it means the string will be palindrome only if the remaining string is palindrome. Okay, now for the remaining string, again do the same thing. Check the first character and the last character of the string. Since these two characters match, again, the string will be palindrome if the remaining string is palindrome. So then go for the next character, which is L and L. These two characters also match. So you will go for the remaining string, which is AYA. Similarly, you will check for A and A, it matches. And since Y is the only string left, so eventually we will be left with a single character string, right? Which is Y. And by default, a single character string is a palindrome string because reversing it will still give you the same character. And this is how you will say that this string is a palindrome string. If you want to write it as an equation, what we will write is, suppose this str represents a string which we are interested in, then we simply need to do is check the first character of this string and the last character of the string. To access the last character of the string, we can compute the length of this string, okay, and record it in some variable L. And therefore, the last string will be L minus 1, last character. So do a check between these two characters, which is compare str of 0 and str of L minus 1. If they happen to be same, then check the string str starting from first character, so str plus 1, up to second last character. So the length will also be reduced by 2, right? And if you pass the same string, sorry, so the length will be reduced by 1. But in case you want to length will be reduced by 2 because you have removed the first character and the second character, so the length will be reduced by 2. Now we will just see whether this string str plus 1 is palindrome or not. Okay? So if this condition is met, we will call the same function but with this new parameter. Now look at the complete function. So here is the complete function. Look at the simple iterative. Is called whether it's palindrome or not, and this is using an iterative approach. It will be returning a value of A. If it is palindrome, it will return 1. If it is not a palindrome, it will return 0. So we are maintaining a flag which maintains the status of this. The string is being pointed by this pointer A, and length is the length of the string. So for I equal to 0, we start from the 0th index and we go up to length by 2, right? Because we are actually checking always the first character with the last character. So we just need to go to the midway of the string. Okay? And now we will check the first ith character with the ith character from the end. And if it is same, then we continue. If it is not same, then definitely the string is not a palindrome string. So we can quit this loop at that very moment. And for this, you will set the flag to 0 because we have found at least one occurrence of a pair of characters which are not same. So we will set flag equal to 0 and we'll quit this loop itself. So we will use break. We will come out of the loop and return the flag. If all the characters matches, then this loop will keep on going and will be like until I becomes less equal to length by 2. In that case, the value flag has not changed and it will return the flag exception saying that the string is palindrome. In case of recursive function solution, we have to take the base case. The base case is what if the string is a ordinary string or an even length string. If it is an even length string, the So suppose we have this string hello, right? Okay, maybe we can consider simple pallindrome as well. H E L E H. Now this is a pallindrome string. So what will happen? This character and these two characters will be compared, and these two characters will be compared. Okay, the length of this string is 5. So the loop will go up till 5 by 2. It's an integer division, which will give you 2. So it will go up to 0, 1 because I was less than this, right? Now, what is eventually left is this, which is a string of length 1. Now, if we have a even length string, then in this case, these two characters will be compared, and these two characters will be compared, and eventually we will left with a null string, right? So, what are the possibilities? So, if the string is a palindrome string, eventually we will have a string of either length 1 or length 0. So, here, that's why the base case in this recursive function is if length is less than equal to 1, that is, either it is a null string or a string of length 1, then these both strings by default are palindrome. So we will return a value of 1. Otherwise, we will check the first and the last character of this string, that is a of 0, will be checked with a of length minus 1. If this comparison fails, that is, these two characters are different, then we will stop this recursive function here itself, similar to the loop case here, and we will return a value of 0. Otherwise, we will call this return recursive is called, that is, we will make a recursive call to the same function again with a shorter string at an index of starting from a plus 1 and with a length of length minus 2. So what will happen here is that suppose you have this string H E H E H, right? And this string is being pointed by a pointer A, right? So basically, this was some string str, and A is storing the address of str. So when you will, so now if we start from the value stored in A, we start from here and we go up till the length. And the length of the string was 5, so we cover the entire string. But in the next call, we go from A plus 1 to 5 minus 2. So it will become, now the string which we will consider will actually start from here and will go to here, the remaining string. So that's why in each recursive call, we are reducing the length of the string by 2. And this will eventually reduce to a string of either length 1 or 0, which will be marked as our base case. The next example for recursion is using arrays. So let's take a small detour and understand arrays for a few minutes before taking into that example. Array is defined as a sequence of elements of similar data type. So if I have, so let's say this is my array A, and it stores elements from 1 to, so these are integers, and here the length of the array is 5. Okay, so, and it is storing all these elements 1, 2, 3, 4, 5, and we have to access any element of this array We can access it using square brackets and passing the index of that specific element. Each element in this array is assigned an index starting from 0. So 1 has an index of 0, 2 has an index of 1, 3 has an index of 2, 4 has an index of 3, and 5 has an index of 4. So here, if I do a of 1, then it will return the value 2. If I do a of 4, it will return the value 5. So array is a sequence, but a collection of multiple elements of same data type stored in a sequential order. Now let's look at the example. The last example we are going to cover for this topic. First, let's talk about linear search. So linear search is that we want to search an element in an array. Now, how can we search an element in an array, right? That's the question. Okay. Suppose in this array, 1, 2, 3, 4, 5, you want to search the element 10. We don't know this element in the array. So we have to we have to compare it with each and every element present in the array. Okay. So what we can do is that when we are comparing this element with each and every element present in this array, we have to traverse this array sequentially, either in this way or in this way, right? We cannot skip any element because we don't know whether it is there or not. And if it is there, then at what index it is there. So we will take the last element, let's say, and compare it with this array. If this element matches to our queried element, then yes, it is found in that specific array. If not, then this element might be present in the remaining array. So what we are doing is that in each iteration, we take array A, we compare with the last element, which is A of length minus 1. So we compare A of length minus 1 with our query element Q. If it is found, then it's good return. If this is not found, then it means that, okay, the last element is not Q, but then it is a possibility that in this array A, from 0 to length minus 2, we might find Q, right? This may be present there. So to see whether Q is present in remaining array or not, we will now do the same thing, but with an array of size 1 less than original size. And we will keep on doing this till we are left with either one element, in which case it will be a simple match, or we can simply quit if the size of the array has finished, right? So there is no more elements to compare, and at that point we will stop searching. So how can we do this using recursion, right? As I said, we will just look at one element in each iteration, and then we have, if the element is found, the search is completed. If the element is not found yet, then we have to search in the remaining array. So this is the basis of the function here, right? So what we will do is, we will call this linear search, okay? And we will, this ARR is representing the array, the int I is representing the index we want to look at, and X is representing the element we are trying to find. So if we are looking at the 0th index, that means, so as you can see here is the length of the array, right? But length minus 1 basically, because it is the index of that particular element, the last element in that array, right? So it's equal to length minus 1. So if I is equal to 0, that is there is only one element, simply compare it with X. If it is found, return 0. If it is not found, return minus 1. Else, what do? You compare ARRI, that is the last element of this array, at index I, where I is representing the index of the last element, with element X. If it is found, return I. If it is not found, then call this function again on the same array, but now the last element becomes I minus 1. So for this new function call, the last element will be present at an index of I minus 1 instead of I, which means we have reduced the size of the array. And then we will search it. Now, the drawbacks of linear search is that even if the array is unsorted, then yes, we can't do anything. We have to search this element again and compare it with each and every element present in this array, right? Because it's unsorted, we don't know where it is. But what if the array is sorted? So suppose I have this array, right? Okay, suppose I have this array 1, 2, 3, 4, 5. Okay. So I have this array 1, 2, 3, 4, 5, and I want to search element 4. Now this array is sorted, okay, and I have this information. So instead of comparing this element 4 again and again with each and every element until and unless I find 4, I can do something smart. I know this is a sorted array. If I select this element 3 and compare it with 4, and this element doesn't match, and this array is sorted in an increasing order, so if 3 is not matching 4, and 3 is less than 4. So it means all the other elements will also be less than 4, right? So we know that 3 is less than 4. 3 is not equal to 4, first of all. So this element and this element doesn't match. Okay. The second case, whether 3 is greater than 4 or less than 4. So 3 happens to be less than 4. So it means all the elements on the left of it will also be less than 4, which implies that 1, 2 will also be less than 4, right? So there is no point of accessing these elements again and, comparing with the queried element. What other thing we can do is, now we can start searching in the right array. That is, now we are sure that this queried element has to be present in the right side of the array, right side of this element 3 and not on the left. Okay. Now again, we can do one more thing. Similarly, in this right array, we don't have to look at each and every element again and again. So what we will do is, we can again split it. We can again look at the middle element, and then we can compare. If there happens to be no middle element, we can take either of the two as the middle element. So we can compare with 4, the match happens, and the search stops. Otherwise, we would have repeated it. So let's look at another example, a very simple example. Suppose the numbers are 10, 14, 10, 14, then 17, then 19, 21, 35, 40. Okay. This is my array. And I am in. Okay. So now in this array, we want to query this element 22. This is a sorted array. The length of this array is 0, 1, 2, 3, 4, 5, 6. Okay. So we have total 7. The length of the array is 7. So the middle element will be 0 plus 6 by 2, which is 3. This will be our middle element. Okay. So we know for sure that the elements on the left will be smaller. The elements on the right will be greater than 19. Okay. Also, why we are taking the middle element? Because this approach helps us in dividing this array exactly into 2 halves, right? So we can easily count half of the elements, depending on whether this element is less than or greater than our element we are looking for. So here 19 happens to be less than this element. So we will look into the right half. The right half being array with only 3 elements, 21, 35, and 40. So here we will now look into this element and again find the middle element, which is 35. We will again compare it with 22. So here and here, the elements will be greater than 35. The elements will be less than 35. Now 35 is greater than 22. So we have to look in the elements which are smaller than 35. So we will now look at the index 21. Now, do note that the array with which we are now left is a single element array. Okay. And we now compare 21 with 22. There is a mismatch. These 21 and 22 are not equal. And also it is a single element array. So we do not have any hope of looking into any other element to see whether 22 exists or not. So with this, we will say that this 22 doesn't belong to array A. So this was accepted by A. And now we can simply say that this 22 is not a member of A. Now, let's look at the program, how to implement it. Again, we will look at the recursive solution here, binary search, and this search is known as a binary search. Binary because we are looking at binary. We are dividing the entire array into two parts, and each time we are only looking into one. This search only works if the array is sorted, either increasing or decreasing, but it has to be sorted. Otherwise, this won't work. The solution has been written assuming it is sorted in increasing order. If you want to make this work for an array which is sorted in decreasing order, you can change it accordingly. Now here, ARR is representing the array in which we have to search the element. X represents the elements to be searched. L represents the lower index of the array we are looking into. And R represents the upper index or the last index of the array we are looking at, right? So what can happen? What are the possibilities? How to decide what can be the basis? So this was an even length array, right? In case of even length array, what eventually happened? We are left with a single element array, right? In this case, L was also 4 and R will also be 4. Now suppose we have an even length array. This was odd length, right? If we have an even length array, so let's say we have this array A, 1, 2, 3, 4, 5, 6. Okay. Suppose we now check with an element we are looking for is 7. We take the element 3, compare it with 7. It doesn't compare. It doesn't match. We look for the right half, the index being L equal to so in this case, L and R we can write, right? So L equal to, here are the actual places 0, 1, 2, 3, 4, 5. So L being 3 and R being 6, 5. Now we will again look at the middle element, which is 5. We'll compare it with 7. It doesn't match. It gives you 6. Okay. It's a single element array, so it will become here again. We will search for this array, which is 5 and 5. Okay. But now what? Suppose a condition may arise when you don't have any specific element to list. So this was actually 6. Now suppose we introduce one more element. Introduce one more element, suppose 8. And now we search into the specific area. Okay? 6 and 8. Now this, when we try to match with 7, it is a mismatch. In that case, L will be 5. Here it will be because we have a rectangle. So now, when we compare with the first element, which is 5, it will say we go to the left, right? Now when it says we go to the left, how will you find the left? That's a question. So the way to find the left index is, what is the middle index? Middle index is 5, right? So whatever was the lower index of this array, which was initially the same 5, you will put the 5. And you want the left array, right? So here we will shift to the 4 here first, and then we look into the like how we can so we find this int mid equal to L plus R divided by 2, right? Now see, maybe we can try to understand it here. Okay, this will be easy. What we are saying is so we have this array A element to be searched, the lower index, the upper index. Now, so how you will find the middle element of the array? Simple. You will do L plus R by 2. If it is an odd length array, you will have exactly one mid element. If it is an even length array, actually there are two elements, but by this formulation, you will take the first element, right? Now, you will compare the middle element with X. If it is happened to be a match, you simply return the index to be the index of the middle element. If it doesn't match you, then we have to do the binary search. So what we will do, we will do the same search, but in one of the halves. Since the middle element is greater than X, we will search in the first half. Right? So how we will decide which is the first half? We have this array. This is L, this is R. Let's say 1, 2, 3, 4, 5, 6, 7, right? So this is my middle index. Now, for this array, for this left half, lower and upper index, this will be L, and the right value has to be M minus 1. So that's why we have called with this, that is L and mid minus 1. In case this happens to be smaller, so you have to search in the right side, which will be basically M plus 1 common. So here, lower index value will change to mid plus 1, and then M. So now you understood this. So here is the example I was talking about to come up with the basis. So if we have exactly with 2 elements, we searched with 6. So we will assume that now we will be searching in the left half. There exists no left half. So how will you ensure there is no left half? So for the left half, what will be the actual value of L and U? So L will remain the same as this call, which is 5. But the upper index will be the index of this element minus 1, which will be 4. So here, what has happened that the lower index has become greater than the right index, which will not be possible, which means that we have already exhausted with the elements to be searched. So that's why if L is greater than R, then in that case, the element was not found because the element has not been found yet. And now there has been no more elements to be searched. So you return minus 1. If L is equal to R, there is still a hope because the array has only one element. And so we will just compare with this one element. And depending on whatever is the outcome, we will return 1 or minus 1. Okay. So here we are returning L because we are interested in the index as well. So we are returning the index of the element at which it is found. So here we are returning L. In case the middle element happens to be the value we are looking for, then we will return the mid. So for recursion, we have seen 3 examples. One using integers, the second one using strings, and the third one using arrays. I'll provide this file in the and will give you the link to this file in the description of the video so that you can actually look at the file and can try to play around by using different value of the array or by looking for different value of X to be searched or by printing different
outputs at different stages of these functions to understand it in detail. So this file will be shared, and the link will be given in the description of the video. So with this, we end the topic of discussion. Topic of today's discussion, which is recursion. Thank you.